So we're looking for a line, but how are we going to find the right line? You may have heard and seen the expression the line of best fit. Well, what does that mean? If you think about it, what criterion do we use to figure out what line best fits the data? Well, there are several criterion we could use and several criteria that have actually been used, but most of them either are end up being not very efficient or they're basically just too vague to be used. For instance, okay, one thing I could say is that, well, I want a line such that there is an equal number of points on both sides. Okay, so for instance, this line might work, right? So it goes exactly through one of the points and has 5 points above it, 5 points below it. But why this line and not this line? Or why this line or not that line? Or since we're at it, why any one of those three lines or not this line? Well, you may say, but this line goes exactly in the opposite direction of the pattern. Yes, but it does fit the criterion, doesn't it? So this criterion of wanting equal number of points on both sides of the line doesn't really work. It's too vague, it's too imprecise, and can lead to some things that we don't really want. Alright, so there are other criteria we can use. Maybe we want a line which is closest to as many points as possible. But here again, what are we going to use? For instance, this line goes pretty close to 4 of the points. That's a pretty good number. But I hope you would agree with me that this line does not really represent the pattern we have in front of us. So this one is not a good idea either. Okay. So some people say, well, it should be some line that cuts through the points in some kind of, well, cuts through what exactly? Okay, people have actually looked at this question a little bit more in depth because at an intuitive level it does make sense. And so what statisticians have come up with is the following idea. What we can do is we can try and encircle all the data through some kind of an ellipse, okay? And then we would have to figure out exactly how. And then once we have that ellipse done, what we can do is we can look at the axis of that ellipse and use that one as the line of best fit. Again, that is an approach which is actually being used, but again, it's not as clean cut, and it's still, people are still working on making this idea work. So in fact, people use a different criterion. Let's have a look at what it is. When you see in research articles the authors claiming that they've done a regression analysis, or they've done some kind of regression line or regression formula or something like this, I bet, and I'm going to win 99.99% of the times, that they're using what is called least squares regression line. Okay, so now this is a very special line, and once I tell you what the criterion is, probably you're not going to be satisfied or happy with it because it's not very intuitive, and also it's not clear why it should be the criterion of choice. But this is what people actually use. Okay, so what do people do? It is, as I said, the most commonly used criterion, and what we try to do here is we choose the line that minimizes a very specific mathematical quantity. What is that quantity? For each one of these points that we see, what we're going to do is we're going to compute the vertical distance from the line that we're looking for. Okay? And then what we're going to do is we're going to compute the square of that measurement. Okay? So that will be the area of the square that has one side joining vertically the dot to the line. So what we're going to do is we're going to do the same thing for each and every one of these dots. Okay, so what we're going to do is we are going to choose the line that minimizes the sum of these squared errors. You can think of each one of those vertical distances as the error, the random variability that has occurred in the observations besides the relationship. So we're going to construct one for this point, one for that point, and one for each and every one of the other points. And we're going to choose the one line for which the sum of these squared errors is actually smallest. Now this may look like a really daunting task, but it turns out, and this is one of the reasons why mathematicians have chosen it, that there is a very clean, a very neat method, computational number crunching method, for identifying what this line is. So why do we use this particular criterion? It doesn't really look comfortable, does it? I mean, it looks really weird. Why should we use this particular criterion? Well, first of all, it is consistent with the assumption that we made earlier that the errors, the random variability is all in y. So what we're going to be doing is we're going to be doing something with the vertical distances from each of the points to the line that we're choosing. So that will tell us that to consider just the vertical variability in y. And secondly, as I said, believe it or not, it's easy to implement numerically. This may look like a really complicated problem. How am I going to choose out of every possible line the one that minimizes that? Well, it turns out number crunchingly, if that's a word, it is fairly easy. So what least squares linear regression does is it uses the data collected to estimate the intercept b, remember that is the output value when the input is equal to 0, and the slope m, that is the output change per unit input increase. So notice that in fact all we're looking for, because we're asking just for a linear relationship, all we're looking for is those two numbers. And it turns out that the formula for those two numbers are fairly easy. Okay? Now, once we have those two numbers, then of course we can generate the formula, right? Y equals mx plus b. How are we going to use that formula? Well, given any input value x, what I can do is I can insert that value into the formula, and I can make a prediction of what the corresponding output value is going to be. So what this technique does, if once it provides us with this formula for the line, that allows us to say, okay, if x is so much, then I expect y to be so much. So think in very simple practical terms. Let's say I can find a least square regression line that tells me what is the relationship between the amount of insulin given and the blood sugar level of the patient. Then this formula, if I can find it, tells me, well, if I give this much insulin to the patient, this is what the blood sugar level is going to be in, say, 10 minutes or 15 minutes or an hour, or whatever you want. Okay? As with many other things that we've done in statistics, we know that restrictions are coming, and in the guise of assumptions. Okay, all of this is going to work as long as the mathematics make sense, and that means as long as certain assumptions are in place. So let's have a look at what these assumptions are, because just like in hypothesis testing, and remember, this is not hypothesis testing we're doing here. This is estimation, right? We're trying to construct something. We're saying, well, how much is it? So once again, just like in hypothesis testing, it works under certain assumptions. This technique also requires certain assumptions. Let's see what they are.